We are going to continue with the series in which we are looking at sequences and series. We will derive the formula for the sum to infinity of a geometric progression. At the end of this lesson, you will be able to derive the formula. You will be able to have an idea of where the formula for the sum to infinity is coming from. In our earlier lessons, we found that the sum of the first n terms of a GP was given by this beautiful formula which we are seeing there. If we expand this formula, it will still be beautiful, but it will be looking somewhat different, but it's the same thing. It's just the expansion. We have expanded the numerator, so we can further manipulate this formula so that we have two algebraic fractions. When we have this formula written in this form, in the form of two algebraic fractions, this will help us derive the formula for the sum to infinity of a geometric progression. Are you sure this is the same sum to infinity? You might ask. Yes, it's the same thing. It's the same thing. So if we make this a single fraction, we'll get back to a minus a r raised to the power n over, which is over 1 minus r. So we use this as our sum of the first n terms. Condition number 1. If r is numerically larger than 1, if the absolute value of the common ratio is greater than 1, we are going to have a situation where r raised to the power n tends towards infinity as n tends towards infinity. As n gets larger and larger, r raised to the power n will also become larger and larger. If we take r, the common ratio, to be equal to 2, say 2 to the power 5, we are going to have a 32. 2 to the power 10, we're going to have 1024. 2 to the power 15, we're going to have 32,768. 2 to the power 20, we're going to have 1,048,576. So as the value of n becomes larger and larger, the common ratio raised to the power n will also become larger and larger. A sub n, the sum of the first n terms, will tend towards infinity as n tends towards infinity. This is the value. This value is becoming larger and larger as n is increasing. So what happens is that this whole algebraic fraction, this whole thing is becoming larger and larger to such an extent that even if we take away a over 1 minus r from this large value, a sub n will still tend towards infinity as n tends towards infinity. We have come to this conclusion before in the previous lesson. We know that Sn has no limiting value because it's getting larger and larger. S sub n is increasing beyond bound. There's no bound. There's no limiting value for it. And if S sub n has no limiting value, we can conclude that for this condition where r is numerically larger than 1, we do not have a sum to infinity. The GP has no sum to infinity. Condition number 2. What if we took values of r that are less than 1, or the values of the common ratio that are between -1 and 1? If we took the absolute value of r which is less than 1, will we have a limiting value? So r raised to the power n will get smaller and smaller as n gets larger and larger. This part here, that part there will get smaller and smaller as n gets larger and larger. That part, r raised to the power n, tends towards 0 as n gets larger and larger because we are getting a common ratio that is between -1 and 1. Let's take r to be half. If we had r being half, 1 over 2 to the power 5 will give us 0.03125. 1 over 2 to the power 10 will be 0.009765625. 1 over 2 to the power 15 will give us 0.000030517578125. 1 over 2 to the power 20 will give us 0.00000095367431640640625. As our value of n is increasing, we took 5, we took 10, we took 15, we took 20. The value of r, the common ratio raised to the power n, is tending towards 0. And if it's tending towards 0, what's happening is that this whole part will be a big 0, and a over 1 minus r minus 0 will just be a over 1 minus r. So what we're saying is that as n gets larger and larger, S sub n, the sum of the first n terms, is tending towards a value, and that value is a over 1 minus r. So S sub n has a limiting value, and if S sub n has a limiting value, that means S sub n has a sum to infinity. The limiting value is a sum to infinity. So the GP will have the sum to infinity, and it is a over 1 minus r. So for the general GP, AR raised to the power 2, and so on, the sum to infinity is a over 1 minus r, provided that r is numerically less than 1, provided that r is between -1 and 1. That is when that formula will work. If r is larger numerically larger than 1, numerically greater than 1, we are not going to use this formula because there is no sum to infinity for an r which is numerically less than 1. I hope you will be able to sit down and derive this formula on your own. I end this one on this note.